We are so alone, not because aliens don't exist, but because the universe itself has made sure we can never reach them. 1 light year is an insurmountable wall, and once you understand why, you'll never look at the night sky the same way again. And here is a question. If you could travel 1 light year per second, where in the universe would you go first? Let us know in the comments. I will pin the most creative answer. Now let's begin. Imagine this. In 1 single second, light could circle Earth 7.5 times. That's the equator, over and over again, in the blink of an eye. Now stretch that speed out for an entire year, 365.25 days. That distance equals about 5.88 trillion miles or 9.46 trillion kilometers. That's 1 light year. To put it another way, if you could drive a car at highway speed without stopping, it would take you over 600 million years to cover 1 light year. Your car would rust away, continents would drift, species would evolve and go extinct, and you'd still be driving. This is the scale we're talking about when we discuss interstellar travel. Scientists have been fascinated by this measurement since the 17th century. Early astronomers realized that the stars were so far away that miles and kilometers became useless. They needed a unit that matched the cosmic scale, so they turned to the one thing that moves faster than anything else: light itself. The closest star system to us, Alpha Centauri, sits about 4.37 light-years away. That means the light you see from Alpha Centauri tonight left that star over 4 years ago. You're literally looking back in time. If an alien civilization lived there and looked at Earth through a powerful telescope, they'd see us as we were 4 years ago. Our news, our actions, our entire world would be on a delay. But here's where it gets wild. Even though Alpha Centauri is our nearest neighbor, the distance is so vast that it defies comprehension. If you stacked $1 trillion bills on top of each other, the pile would reach about 67,000 miles high. Now multiply that by almost 90. That's roughly 1 light year. And we're talking about traveling even farther. Now you might be thinking, we've sent spacecraft beyond our solar system, right? Yes, we have. Voyager 1, launched back in 1977, is currently the farthest human-made object from Earth. It's been traveling for nearly 50 years, cruising through interstellar space, carrying messages from humanity on its golden record. But here's the kicker. Voyager 1 has traveled roughly 14.5 billion miles from Earth. That sounds like a huge number, and it is by earthly standards. But in cosmic terms, it's barely left the neighborhood. Voyager 1 has covered only about 0.0025 light-years. After nearly half a century of travel, it hasn't even reached 1/400th of a light-year. At its current speed of about 38,000 miles per hour, Voyager 1 would take over 70,000 years to travel just 1 light-year. Let that sink in. 70,000 years. Humanity didn't even have written language 70,000 years ago. We were still learning to make tools from stone. The pyramids wouldn't be built for another 67,000 years. And Voyager 1 is slow by modern standards. Let's talk about the fastest spacecraft humanity has ever built, NASA's Parker Solar Probe. This engineering marvel was designed to study the Sun up close, diving repeatedly into its scorching outer atmosphere, the corona. To do this, it needed to move at incredible speeds. On December 24, 2024, the Parker Solar Probe shattered its own record. It reached a blistering speed of 192 kilometers per second, or about 430,000 miles per hour. That's the fastest any human-made object has ever traveled. At that speed, you could fly from New York to Tokyo in less than a minute. But even at this record-breaking velocity, the Parker Solar Probe would still take over 6,500 years to cover just 1 light year. Think about that, 6.5 millennia. When that journey began, humans would be building the first cities in Mesopotamia. Writing would just be invented. By the time the probe arrived, entire civilizations would have risen and fallen. If you're enjoying this journey through the cosmos, please hit that subscribe button and give this video a thumbs up. It helps more people discover these incredible cosmic truths, and it keeps this channel growing. Now let's dig deeper into the challenge. Why is speed such a problem? It all comes down to physics. Specifically, Newton's laws of motion and Einstein's theory of relativity. When you want to move faster in space, you need to push against something. Rockets work by expelling mass in one direction to move in the opposite direction. It's basic action and reaction. But there's a catch. The faster you want to go, the more energy you need, and that relationship isn't linear, it's exponential. Doubling your speed doesn't just double the energy required, it quadruples it. Want to go 10 times faster? You need 100 times more energy. This is why reaching even a fraction of light speed seems impossible with our current technology. Let's do some quick math. The Parker Solar Probe, traveling at 192 kilometers per second, is moving at about 0.064% of the speed of light. That's not even 1/10 of 1%. To reach just 10% of light speed, we'd need to go over 150 times faster than the Parker Solar Probe. The energy required for that is staggering. We're talking about energies equivalent to thousands of nuclear bombs just to accelerate a small spacecraft. And that's only getting up to 10% of light speed. Even at that velocity, crossing 1 light year would still take 10 years. Reaching another star system, decades at minimum. But wait, there's more. It's not just about acceleration, it's also about fuel. Every rocket carries its fuel with it. The more fuel you carry, the heavier your spacecraft becomes. The heavier your spacecraft, the more fuel you need to accelerate it. Now, this is called the tyranny of the rocket equation, and it's one of the fundamental barriers to interstellar travel. Imagine trying to pack enough fuel for a journey lasting thousands of years. The fuel tanks alone would be enormous, requiring even more fuel to move them. You quickly reach a point where the spacecraft becomes so massive that no amount of fuel can accelerate it to the speeds you need. It's a vicious cycle that traps us in our solar system. Scientists have proposed some creative solutions to this fuel problem. One idea is the ion drive, which uses electricity to accelerate ions and create thrust. Ion drives are incredibly efficient compared to chemical rockets. NASA's Dawn spacecraft used ion propulsion to explore the asteroid belt, visiting both Vesta and Ceres between 2011 and 2018. But here's the limitation. Ion drives produce very little thrust. They're great for slow, steady acceleration over long periods, but they're not powerful enough to reach the speeds we'd need for interstellar travel within a human lifetime. Dawn's ion engine could accelerate the spacecraft by about 60 miles per hour over 4 days of continuous operation. That's slower than a bicycle. Another concept is nuclear propulsion. Instead of chemical reactions, you'd use nuclear fission or even fusion to generate thrust. The advantage is that nuclear reactions release millions of times more energy per unit of fuel than chemical reactions. A nuclear rocket could theoretically achieve much higher speeds than anything we have today. NASA and other space agencies have been studying nuclear propulsion since the 1950s. Project Orion, conceived in the late 50s and early 60s, proposed using nuclear bombs. Yes, actual atomic bombs detonated behind a spacecraft to push it forward. The design called for dropping bombs out the back, detonating them, and riding the shockwave like a surfer on an explosive wave. The calculations showed that Project Orion could reach about 5% of light speed. That would cut the travel time to Alpha Centauri down to around 87 years, still a lifetime, but at least within the realm of possibility for multi-generational missions. However, the project was abandoned due to the Nuclear Test Ban Treaty of 1963, which prohibited nuclear explosions in space. More recently, scientists have revisited nuclear propulsion with safer designs. Nuclear thermal rockets heat propellant using a nuclear reactor instead of chemical combustion. Nuclear electric rockets use a reactor to generate electricity, which then powers ion drives or other electric propulsion systems. These technologies could potentially double or triple the speeds we achieve with chemical rockets. But even with nuclear propulsion, we're still talking about journeys lasting decades or centuries. And that brings up another massive challenge: time. Human lifespans are limited. Even if we could build a spacecraft capable of reaching 10% of light speed, the journey to the nearest star would take over 40 years. The astronauts who left Earth would be elderly or dead by the time they arrived. This has led to the concept of generation ships. These would be enormous spacecraft, essentially flying cities, that could support multiple generations of humans. The people who started the journey would have children, who would have children, who would eventually arrive at the destination. It's a beautiful and haunting idea, a whole society living and dying in the void between stars. But generation ships face enormous challenges. You'd need to create a completely self-sustaining ecosystem. That means growing food, recycling air and water, managing waste, and maintaining technology for centuries without any possibility of resupply or repair from Earth. One critical failure could doom everyone aboard. There's also the psychological aspect. Humans evolved on Earth with open skies, natural landscapes, and the freedom to roam. What would happen to people born and raised in a metal cylinder, knowing they'd never feel wind on their face or see a sunset that wasn't projected on a screen? Would they even want to continue the mission their ancestors started? Some scientists have proposed cryogenic sleep or suspended animation as a solution. If we could put astronauts into a state of hibernation, they could sleep through the journey and wake up at their destination, barely aged. This idea has been a staple of science fiction for decades, from Alien to Interstellar to Passengers. But here's the reality: we don't have the technology to safely freeze and revive humans. We can preserve cells and small organisms at extremely low temperatures, but freezing an entire human body causes ice crystals to form, which damage cells and tissues. Thawing would likely be fatal. Research into therapeutic hypothermia and suspended animation is ongoing, but we're nowhere near ready for interstellar hibernation. Even if we solve the technical challenges of propulsion, life support, and time, there's another problem: navigation. Space is not empty. It's filled with dust, gas, and countless tiny particles. At extremely high speeds, even a grain of sand becomes a devastating projectile. Hitting a pebble-sized rock at 10% of light speed would release energy equivalent to several tons of TNT. This means any interstellar spacecraft would need heavy shielding to protect it from impacts. But shielding adds mass, which brings us back to the fuel problem. Some designs propose using magnetic fields to deflect charged particles, similar to how Earth's magnetosphere protects us from solar wind. But magnetic fields don't stop neutral particles or larger objects. Then there's the issue of communication. Radio signals travel at the speed of light, which sounds fast, until you remember we're talking about light years of distance. If you sent a message to a spacecraft 1 light year away, it would take 1 year to reach them and another year for their reply to come back. A simple "How are you doing?" would take 2 years to answer. This communication lag creates serious problems for mission control. If something goes wrong, there's no way to provide real-time assistance. The crew would be completely on their own, making life or death decisions with no guidance from Earth. They'd be more isolated than any humans in history, true pioneers in the deepest sense of the word. Now let's talk about relativity, because Einstein throws another wrench into our plans. According to special relativity, as you approach the speed of light, strange things happen. Time itself begins to slow down relative to outside observers. This is called time dilation, and it's been proven by experiments with atomic clocks on fast-moving aircraft and satellites. If a spacecraft could somehow reach 90% of light speed, time aboard would pass much slower than on Earth. A journey that takes 40 years from Earth's perspective might only feel like 18 years to the astronauts. At 99% of light speed, that same 40-year journey would feel like just 5.5 years to the crew. This sounds like a good thing, right? The astronauts age less, so the journey feels shorter to them. But there's a heartbreaking consequence. Everyone they left behind on Earth ages normally. By the time they reach their destination and send a signal home, decades or even centuries will have passed on Earth. Their families, friends, everyone they knew would be long gone. This creates a profound isolation. You're not just leaving Earth, you're leaving your entire time period. You become a time traveler of sorts, jumping forward into Earth's future while experiencing less time yourself. It's a one-way trip, not just in space, but in time as well. And here's the real kicker about relativity. As you approach light speed, your mass effectively increases. This means you need even more energy to keep accelerating. The closer you get to light speed, the more energy you need, until at exactly light speed, you'd need infinite energy. It's literally impossible for anything with mass to reach the speed of light. This is why light itself can travel at light speed. Photons have no mass. They're pure energy, but anything physical, anything made of matter like atoms and molecules, can never quite reach that ultimate speed limit. We're forever bounded by the laws of physics, trapped below light speed no matter how advanced our technology becomes. So if conventional rockets won't work, what about alternative propulsion methods? Scientists have dreamed up some wild ideas that sound like pure science fiction, but are actually based on real physics. One of the most promising concepts is the solar sail. Instead of carrying fuel, a solar sail uses light itself as propulsion. Here's how it works. Light carries momentum. When photons from the sun hit a reflective surface, they push against it, just like wind pushing against a sail on a boat. The push from each individual photon is incredibly tiny, but if you make your sail large enough and light enough, those tiny pushes add up over time. The beauty of solar sails is that they never run out of fuel. As long as light is hitting the sail, you're accelerating. Near Earth, that acceleration is extremely small, less than 1 millimeter per second squared, but in the vacuum of space, with no friction to slow you down, you just keep speeding up hour after hour, day after day, year after year. Japan's Icarus mission, launched in 2010, became the first spacecraft to successfully demonstrate solar sail propulsion in interplanetary space. The sail was just 46 feet across, about the size of a large room, and it successfully traveled to Venus using only sunlight for propulsion. It proved the concept works. But there's a problem with solar sails for interstellar travel. The farther you get from the sun, the weaker the light becomes. By the time you're beyond the outer planets, sunlight is so dim that it provides almost no push at all. Your acceleration drops to nearly nothing and you're left coasting. You'd pick up some speed in the inner solar system, but not nearly enough to reach another star in a reasonable time. That's where laser-pushed light sails come in. This is one of the most exciting concepts in modern space exploration. Instead of relying on sunlight, you'd use powerful lasers stationed on Earth or in orbit to push the sail. The breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and investor Yuri Milner, plans to do exactly this. The idea is to build thousands of tiny spacecraft, each weighing just a few grams, with light sails about 13 feet across. Then you'd aim an enormous laser array at them, delivering about 100 gigawatts of power. That's roughly equivalent to the entire output of a large nuclear power plant, focused into a beam hitting a sail the size of a small room. Under this intense laser bombardment, the tiny spacecraft would accelerate to about 20% of light speed within minutes. 20% of light speed, that's fast enough to reach Alpha Centauri in just 20 years. The spacecraft could send back pictures and data, giving us our first close-up look at an alien star system within our lifetimes. But before you get too excited, there are massive engineering challenges. First, you'd need to build laser arrays with a combined power output equivalent to a nuclear reactor. Then you'd need to keep all those lasers perfectly focused on a target that's rapidly accelerating away from Earth. Any misalignment, and you miss the sail entirely, wasting all that energy. Second, the spacecraft would be so small and light that they couldn't carry much in the way of instruments or communication equipment. They'd essentially be flyby probes racing past Alpha Centauri at 20% of light speed, snapping a few pictures and beaming the data back to Earth. No landing, no exploration, just a cosmic drive-by shooting photos through the window. Third, there's no way to slow down. Once you're moving at 20% of light speed, you're committed. You can't fire brakes in space. You'd zip right past your target and keep going into the depths of the galaxy. The entire mission would capture maybe a few hours of data as the probe screamed past the star system. Still, Breakthrough Starshot represents our most realistic shot at reaching another star within a human lifetime. It's a testament to human ingenuity. If we can't make big, heavy spacecraft go fast, we'll make tiny, light spacecraft and push them with lasers. Sometimes, the solution to an impossible problem is to completely reimagine what you're trying to do. Another exotic propulsion concept is the antimatter rocket. Antimatter is like matter's evil twin. For every particle, there's an antiparticle with opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. Einstein's famous equation, E equals mc squared, tells us that mass can convert to energy, and antimatter does this with perfect efficiency. A single kilogram of antimatter, when it annihilates with a kilogram of regular matter, releases about 43 megatons of energy. That's roughly the yield of the largest nuclear weapon ever tested, the Soviet Tsar bomber. Now imagine harnessing that energy for propulsion. An antimatter rocket could theoretically reach a significant fraction of light speed. The challenge is that antimatter doesn't exist naturally on Earth. We have to create it using particle accelerators, and the process is incredibly inefficient and expensive. CERN, the European Organization for Nuclear Research, can produce antimatter, but only in tiny amounts. Creating just 1 gram of antimatter would cost about $62 trillion with current technology. Even if we could produce antimatter cheaply, storing it is another nightmare. Antimatter annihilates instantly upon touching regular matter, so you can't just put it in a regular container. Scientists have developed magnetic traps that can hold antimatter particles suspended in a vacuum, but only in microscopic quantities for short periods. Storing kilograms of antimatter for an interstellar journey is far beyond our capabilities. Then there are truly speculative ideas, concepts that push the boundaries of known physics. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, would create a warp bubble around a spacecraft. Space in front of the ship would contract, while space behind it would expand, effectively moving the bubble faster than light without the ship itself ever accelerating. It sounds like Star Trek, and there's a reason for that. The Alcubierre drive is literally inspired by the warp drives in science fiction. But here's the wild part. It doesn't actually violate Einstein's relativity. The ship isn't moving through space faster than light. Space itself is moving, carrying the ship along like a surfer on a wave. The problem is that the Alcubierre drive requires exotic matter with negative energy density. We're not even sure such matter exists. Some quantum field theory suggests it might be possible under extremely specific conditions, but creating and controlling it at the scales needed for a warp drive is purely theoretical. We have no idea how to actually build one. Even if we could, the energy requirements are astronomical. Early calculations suggested you'd need more energy than exists in the observable universe. Later refinements brought that down to something like the mass energy of Jupiter. Still impossible with foreseeable technology, but at least theoretically possible if we could somehow harvest and convert an entire gas giant. Wormholes are another theoretical possibility. These are shortcuts through space-time, like tunnels connecting two distant points in the universe. If you could create or find a stable wormhole, you could step through and instantly emerge light-years away, bypassing the speed limit entirely because you're not actually traveling through normal space. Einstein's equations actually allow for wormholes. They're a valid mathematical solution to general relativity. But there's a massive gap between mathematical possibility and physical reality. Every attempt to model a stable, traversable wormhole requires exotic matter with negative energy to keep the tunnel from collapsing. Once again, we're back to something we don't know how to create or even if it exists. And even if wormholes exist naturally somewhere in the universe, finding one would be like looking for a specific atom in an ocean. They'd probably be microscopic, unstable, and located in the most extreme environments imaginable, like near black holes or neutron stars. Capturing one, enlarging it, stabilizing it, and moving it to where we need it seems absurdly beyond our reach. Let's take a step back and consider the sheer emptiness of space. We often see beautiful images of nebulae, star clusters, and galaxies glowing with vibrant colors. These images make space look crowded and alive, but the reality is that space is almost incomprehensibly empty. The distances between objects are so vast that emptiness is the defining characteristic of the cosmos. Our solar system is a perfect example. The Sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, comets, and dust combined, makes up less than 1/5 of 1%. And all of this matter is spread across a region billions of miles wide with mostly nothing in between. The average distance between stars in our galactic neighborhood is about 5 light-years. Imagine shrinking the Sun down to the size of a grain of sand. On that scale, Earth would be invisible, smaller than a speck of dust, orbiting about an inch away. The nearest star, Alpha Centauri, would be another grain of sand 4 miles away. 4 miles of empty space between grains of sand. That's how lonely space truly is. When we zoom out to the galactic scale, it gets even more extreme. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. That sounds crowded, but the galaxy is about 100,000 light-years across. If you calculated the average density, you'd find that space inside a galaxy is still overwhelmingly empty. Between galaxies, the emptiness is even more profound. The nearest major galaxy to us, Andromeda, sits about 2.5 million light-years away. That's the distance light travels in 2.5 million years. Between the Milky Way and Andromeda, there's mostly nothing. A few dwarf galaxies, some scattered stars, thin wisps of gas, but mostly just void, stretching for millions of light-years. This emptiness has profound implications for interstellar travel. You can't stop for supplies. You can't pull over if something breaks. There are no rest stops, no repair stations, no helpful aliens waiting to give you directions. Once you leave the solar system, you're on your own in a way that's difficult for humans to comprehend. Every human who has ever lived, except for a handful of astronauts, has lived and died on Earth's surface. Even the astronauts who went to the moon, the farthest any human has traveled, were only about 240,000 miles from home. That's roughly 1.3 light seconds away. They could communicate with Earth with just a few seconds of delay. Compare that to an interstellar journey. The astronauts would watch Earth shrink to a point of light, then fade into the star field, indistinguishable from billions of other stars. They'd be months, then years, then decades of travel time away from home. The psychological weight of that isolation is something we've never experienced as a species. This brings us to another fundamental barrier: biology. The human body evolved for life on Earth. We need oxygen to breathe, water to drink, food to eat. We need gravity to maintain bone density and muscle mass. We need protection from radiation. We need the right temperature and pressure. Earth provides all of this naturally, but space provides none of it. Long-duration spaceflight takes a serious toll on the human body. Astronauts on the International Space Station, orbiting just 250 miles above Earth, experience bone loss, muscle atrophy, vision problems, and immune system changes after just a few months in microgravity. They exercise for hours every day just to slow the deterioration, and they still need months of recovery when they return to Earth. Now imagine spending years or decades in space. Your bones would become brittle, your muscles would waste away despite exercise, your cardiovascular system would weaken, cosmic radiation would damage your DNA, increasing cancer risk. Even with artificial gravity from rotating spacecraft, we don't fully understand the long-term effects of living away from Earth. Then there's radiation, one of the biggest threats to interstellar travelers. Earth's magnetic field and atmosphere protect us from most cosmic radiation. In space, especially in interstellar space, far from any star's protective influence, radiation levels are much higher. Astronauts would need heavy shielding, which again adds mass to the spacecraft. Galactic cosmic rays, high-energy particles from exploded stars and other cosmic events, can penetrate deep into matter. Some of these particles are so energetic that stopping them requires meters of shielding. Astronauts on a journey to Mars, just a few months away, would receive radiation doses equivalent to getting hundreds of chest X-rays. An interstellar journey lasting decades would expose travelers to far more. DNA damage from radiation can cause cancer, cardiovascular disease, and neurological problems. It could affect fertility, potentially preventing a generation ship's population from reproducing. We'd need to develop better shielding technology, perhaps using water, hydrogen-rich materials, or even electromagnetic fields to deflect charged particles. But every solution adds complexity and mass. Food is another critical challenge. The International Space Station receives regular resupply missions from Earth, bringing fresh food, water, and equipment. An interstellar mission would have no such luxury. The crew would need to grow all their own food in space, creating a completely closed ecosystem where nothing is wasted. NASA and other space agencies have been experimenting with space agriculture for years. Astronauts have successfully grown lettuce, radishes, peppers, and other crops aboard the ISS. But growing enough food to sustain a crew for decades or centuries requires massive greenhouses, careful management of resources, and redundant systems in case something fails. You'd need to recycle everything. Water from humidity, sweat, and even urine would be purified and reused. Organic waste would be composted and used as fertilizer. Carbon dioxide exhaled by the crew would be absorbed by plants and converted back to oxygen. The entire spacecraft would become a miniature biosphere, a tiny bubble of life in the cosmic void. But closed ecosystems are notoriously difficult to maintain. Biosphere 2, an experimental facility in Arizona built in the late 1980s, tried to create a completely sealed ecosystem with 8 people living inside. The experiment faced numerous problems. Oxygen levels dropped, carbon dioxide accumulated, species went extinct, and the project ultimately couldn't sustain itself without outside intervention. If we can't maintain a closed ecosystem on Earth, where we have unlimited resources and can open the doors if something goes wrong, how can we expect to do it on a spacecraft millions or billions of miles from home? One equipment failure, one crop disease, one unexpected chemical imbalance could cascade into catastrophe. Then there's the question of maintenance and repair. Spacecraft are complex machines with thousands of components, any of which could fail. On Earth, if something breaks, you call a technician, order replacement parts, and fix it. In interstellar space, you have only what you brought with you and whatever you can manufacture on board. This means an interstellar spacecraft would need to be almost entirely self-sufficient. It would need workshops, raw materials, 3D printers, and crew members trained in every aspect of the ship's operation. The crew would need to be engineers, doctors, farmers, scientists, and mechanics all at once. They'd need to pass this knowledge to the next generation, maintaining expertise over centuries. Space agencies have studied these challenges extensively. The concept of an interstellar arc or generation ship has been refined through countless papers and proposals. But each solution to one problem creates new problems. Add more supplies, the ship becomes heavier. Add more people for genetic diversity and specialized skills. You need more food, water, and living space. It's a cascade of complexity. Let's talk about the psychological and social challenges of interstellar travel, because in many ways, these might be even harder to overcome than the technical problems. Humans are social creatures. We evolved in tribes, in communities, surrounded by nature and open spaces. How would people cope with being confined to a spacecraft for their entire lives? Studies of isolated communities like Antarctic research stations and submarines give us some clues. People in these environments can experience something called the third quarter phenomenon, where morale hits its lowest point about 3/4 of the way through a long mission. Conflict increases, depression becomes more common, and people start to mentally check out. Now imagine that effect stretched over not months, but years or entire lifetimes. The people born on a generation ship would never experience Earth. They'd grow up in artificial environments under artificial lights, breathing recycled air. Their entire world would be the ship. Earth would be a story their parents told them, a distant memory from a place they'd never see. Would they feel connected to the mission? Would they want to continue traveling to a destination they'd never reach? Or would resentment build, generations rebelling against a journey they never chose? These aren't just hypothetical questions. They strike at the heart of what it means to be human, to have freedom and purpose. There's also the question of social structure. How would you govern a generation ship? Democracy works when people have shared experiences and values, but generations born in space might develop completely different perspectives from those who remember Earth. Would the original mission parameters still matter 100 years into the journey, 200 years? Genetic diversity is another critical concern. A population needs a certain minimum size to avoid inbreeding and maintain genetic health over many generations. Studies suggest you'd need at least several hundred unrelated individuals, possibly thousands, to ensure long-term genetic viability. That means a generation ship would need to be enormous, with life support and resources for a small town's worth of people. But larger populations create more social complexity. You'd need governance structures, conflict resolution systems, educational institutions, and cultural traditions. You'd essentially be creating a complete society in a bottle, isolated from the rest of humanity for centuries. The social engineering required might be more challenging than the actual engineering of the spacecraft. Religion, culture, and identity would evolve in unique ways. Cut off from Earth, the ship's population would develop their own traditions, beliefs, and values. They might drift so far from Earth culture that by the time they reach their destination, they'd be almost alien to any humans who might have followed them or developed faster technology to arrive first. That's another sobering thought. Technology advances exponentially. A generation ship leaving Earth today with technology that takes centuries to reach Alpha Centauri might be overtaken by a faster ship launched decades later with better propulsion. The people on the first ship could arrive at their destination only to find colonists from Earth who got there years earlier using superior technology. This is sometimes called the weight calculation problem. When should we launch an interstellar mission? If we wait for better technology, we could get there faster. But if we wait too long, we might never leave because there's always something better on the horizon. It's a paradox that has no clear answer. Let's consider the cosmic perspective for a moment. We've been talking about traveling 1 light year as if it's the ultimate goal, but in reality, it's just the beginning. The Milky Way galaxy is 100,000 light years across. Our neighboring galaxy, Andromeda, is 2.5 million light years away. The observable universe extends for about 46 billion light years in every direction. Even if we could travel at the speed of light, which we've established is impossible for anything with mass, we could only explore a tiny fraction of the universe in a human lifetime. We'd be confined to our local neighborhood, the nearby stars within a few dozen light years. The vast majority of the cosmos would remain forever out of reach. This is a humbling realization. We live in a universe that is fundamentally inaccessible to us. The light from distant galaxies takes billions of years to reach us. We're seeing those galaxies as they were in the ancient past, when the universe was young. Some of those galaxies don't even exist anymore. They've collided, merged, or been torn apart by cosmic forces. And because the universe is expanding, those distant galaxies are moving away from us faster than light. Not because they're moving through space faster than light, but because space itself is expanding between us and them. There's a cosmic horizon beyond which we can never reach, no matter how advanced our technology becomes. Those regions of the universe are lost to us forever. This expansion is accelerating, driven by something we call dark energy. We don't really understand what dark energy is. It's a placeholder name for whatever is causing the universe to expand faster and faster. As time goes on, more and more of the universe slips beyond our cosmic horizon, becoming unreachable even in principle. In a strange way, we're living in a special time in cosmic history. We can still see light from the early universe, from the Big Bang itself, in the form of the cosmic microwave background. We can observe galaxies billions of light years away. But trillions of years in the future, after all the stars have burned out and galaxies have drifted apart, any civilizations that might exist will see a dark, empty universe with almost no visible stars or galaxies. They'd have no way to know the universe was ever different. They'd have no evidence of the Big Bang, no distant galaxies to observe. Their cosmology would be fundamentally limited by when and where they exist in the universe's timeline. It makes you wonder what we might be missing, what evidence of the universe's history has already slipped beyond our reach. But let's bring it back to our original question. Why is traveling 1 light year impossible for humans? We've covered the technical reasons, the enormous distances, the energy requirements, the limitations of physics. We've discussed the biological and psychological challenges. But there's something deeper here, something worth contemplating. The universe is structured in a way that creates islands of existence. Stars are separated by light years. Galaxies are separated by millions of light years. The speed of light limit and the vast distances between objects mean that life, wherever it emerges, is fundamentally isolated. We can observe the universe, but we cannot easily explore it. This isolation might be a feature, not a bug. If interstellar travel were easy, the galaxy would likely be teeming with expanding civilizations, colonizing every available star system. But we see no evidence of that. The Fermi paradox asks, where is everybody? If intelligent life is common, why haven't we detected any signs of alien civilizations? Maybe the answer is simply that interstellar travel is so difficult that civilizations rarely, if ever, attempt it. The barriers we've discussed, the energy requirements, the timescales, the isolation, apply to any civilization bound by the same physics we are. Perhaps we're all confined to our home star systems, looking out at the cosmos but unable to reach across the void. Or maybe some civilizations do find a way. Maybe there are solutions we haven't thought of yet, loopholes in physics we haven't discovered. Maybe advanced civilizations use technologies that seem like magic to us, bending the rules of space and time in ways we can't yet imagine. The universe has surprised us before with phenomena we never predicted. After all, 100 years ago we didn't know about black holes, dark matter, dark energy, or the expansion of the universe. We didn't understand quantum mechanics or relativity. We thought the Milky Way was the entire universe. Our understanding of reality has been revolutionized multiple times, and there's no reason to think we've figured everything out now. Let's explore some of the most cutting-edge research happening right now, work that might eventually contribute to solving the interstellar travel puzzle. Scientists around the world are pushing the boundaries of what's possible, and while we're still far from traveling even 1 light year, the progress is fascinating. The Breakthrough Starshot project I mentioned earlier is one of the most ambitious initiatives currently underway. Announced in 2016, it's backed by some of the biggest names in science and technology. The goal is to send tiny spacecraft to Alpha Centauri within a generation, accelerated by powerful laser arrays to 20% of light speed. The technical challenges are staggering. The light sail needs to be incredibly reflective, incredibly light, and incredibly durable. It has to survive the intense laser bombardment during acceleration without tearing, melting, or deforming. It needs to maintain its shape across 4 light-years of space through micrometeorite impacts and the harsh radiation environment of interstellar space. The spacecraft itself, called a Starship, would weigh just a few grams. That's less than a quarter. Into that tiny mass, engineers need to pack cameras, sensors, communication equipment, power systems, and navigation. It's nanotechnology at its most extreme, pushing the absolute limits of miniaturization. And it all needs to function perfectly after 20 years of travel through the void. Communication presents another enormous challenge. The Starship would be so small that its transmitter would be incredibly weak. By the time the signal traveled 4.37 light-years back to Earth, it would be almost unimaginably faint. We'd need enormous radio telescopes and incredibly sensitive receivers to pick up the signal from all that cosmic noise. And remember, the signals would take over 4 years to reach us. The probe would fly past Alpha Centauri, capture data during a brief window of observation, and begin transmitting. Then we'd wait 4 years for the first images and measurements to arrive. It would be like watching a slideshow with a 4-year delay between each image. The patience required is almost superhuman. Yet, despite these challenges, Breakthrough Starshot represents our best near-term hope for reaching another star system. The physics works, the concept is sound. It's just a matter of engineering, funding, and time. If successful, it would be one of humanity's greatest achievements, our first tentative step beyond the solar system into the wider galaxy. Other research focuses on more speculative propulsion methods. The EM drive, proposed in the early 2000s, claimed to produce thrust without propellant by bouncing microwaves around inside a closed chamber. If true, it would violate conservation of momentum, one of the most fundamental principles in physics. Multiple teams tested the device, and while some reported tiny amounts of thrust, subsequent analysis suggested the results were experimental error. This is how science works. Someone proposes an idea that seems to violate known physics. The scientific community tests it rigorously, trying to replicate the results. If it consistently fails under proper conditions, the idea is rejected. It's disappointing when exciting claims don't pan out, but this process protects us from pursuing dead ends and wasting resources on impossible technologies. More promising is research into advanced nuclear propulsion. NASA's recent investments in nuclear thermal rockets could revolutionize deep space exploration. These engines heat hydrogen propellant using a nuclear reactor, achieving exhaust velocities 2 to 3 times higher than chemical rockets. While still not fast enough for comfortable interstellar travel, they could dramatically reduce travel times within our solar system. DARPA, the Defense Advanced Research Projects Agency, has partnered with NASA on the Draco program, demonstration rocket for agile cislunar operations, planning to test a nuclear thermal rocket in space by 2027. If successful, this technology could enable crewed missions to Mars in months rather than years, establishing infrastructure for more ambitious deep space missions. Fusion propulsion is another area of active research. Unlike fission, which splits heavy atoms like uranium, fusion combines light atoms like hydrogen into helium, releasing enormous amounts of energy. It's the same process that powers the sun. If we could harness fusion for propulsion, we'd have a much more efficient and powerful engine than anything available today. The challenge is that fusion is incredibly difficult to achieve and sustain. You need to heat hydrogen isotopes to millions of degrees, creating a plasma so hot that it would vaporize any material container. Scientists use powerful magnetic fields to contain the plasma, but achieving sustained fusion that produces more energy than it consumes has been the holy grail of physics for decades. However, progress is accelerating. The National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition in December of 2022, producing more energy from fusion than the lasers put into the reaction. It was the first time in history we've achieved net energy gain from fusion. While this was inertial confinement fusion, different from the magnetic confinement needed for propulsion, it proved that controlled fusion energy production is possible. Private companies like Commonwealth Fusion Systems, TAE Technologies, and Helion Energy are racing to develop commercially viable fusion reactors. If they succeed, fusion could revolutionize not just space travel, but energy production on Earth. Fusion produces no greenhouse gases, no long-lived radioactive waste, and uses fuel that's abundant in seawater. It could provide clean, virtually limitless energy. A fusion-powered spacecraft could theoretically reach 10% of light speed or more, cutting the travel time to Alpha Centauri to around 40 years. Still a lifetime, but within the range of a long human mission or a well-designed hibernation system. Combined with advances in life support, artificial gravity, and radiation shielding, fusion propulsion might make interstellar travel feasible within this century. But even with all these technological advances, we're still talking about journeys lasting decades. The fundamental barrier is physics itself. Einstein's speed limit is absolute. No matter how clever our engineering, no matter how much energy we harness, we cannot accelerate matter to or beyond the speed of light. The laws of the universe impose limits that technology alone cannot overcome. This brings us to a profound question. Are we looking at the problem the wrong way? Maybe physical travel isn't the answer. Maybe the future of space exploration isn't sending humans across the stars, but sending information instead. Perhaps consciousness itself could be transferred, uploaded, or transmitted as data. This is pure speculation bordering on philosophy rather than science. But consider this. Everything you are, your memories, personality, thoughts, and feelings, emerges from the physical structure and activity of your brain. Your consciousness is information encoded in neurons and their connections. In principle, if we could map that information completely, we could store it, transmit it, even recreate it. If we reached that level of technology, we could send the information that defines a person to another star system at the speed of light. A laser communication system could transmit the data in years rather than decades or centuries. At the destination, some kind of automated system could reconstruct the person, either as a biological being grown from transmitted genetic information, or as a digital consciousness in a simulated environment. This sounds like science fiction, and it is. We're nowhere near having the technology to map a complete human consciousness, let alone transfer or recreate it. The human brain contains roughly 86 billion neurons, each connected to thousands of others through trillions of synapses. Mapping all those connections, the connectomy, is a monumental challenge, but progress is being made. The Human Connectome Project, launched in 2010, has mapped neural pathways in the human brain at unprecedented resolution. Researchers have completely mapped the connectome of simpler organisms like the roundworm C. elegans, which has just 302 neurons. We're learning how to read and even write information directly to neurons using optogenetics and other techniques. Still, there's a vast chasm between mapping neural connections and capturing the essence of consciousness. We don't even fully understand what consciousness is or how it emerges from physical processes. The hard problem of consciousness, why we have subjective experiences at all, remains one of the deepest mysteries in science and philosophy. Even if we could somehow map and transmit consciousness, profound philosophical questions arise. If you transmit your consciousness to another star and reconstruct it there, is it really you, or is it a copy, while the original you remains behind or ceases to exist? Does the question even matter if the copy has all your memories and genuinely believes it's you? These are questions that philosophy has grappled with for centuries in different forms. The ship of Theseus paradox asks, if you replace every plank in a ship over time, is it still the same ship? If you gradually replace every neuron in your brain with artificial ones that function identically, at what point, if any, do you stop being you? There's no universally accepted answer. Some philosophers argue that identity is about continuity of consciousness, the unbroken stream of subjective experience. Others say it's about physical continuity, that you are your specific atoms and molecules. Still others take a more pragmatic view. If it looks, acts, and thinks like you with all your memories and personality, then it is you in any meaningful sense. These aren't just abstract philosophical puzzles. If humanity seriously pursues interstellar exploration, we'll need to confront these questions. Should we send physical humans on generation ships, knowing they and their descendants will spend lifetimes in transit? Should we send frozen embryos to be raised by robots at the destination? Should we send AI probes to establish infrastructure before humans arrive? Each approach raises different ethical and practical challenges. Let's consider artificial intelligence more seriously. AI is advancing at an incredible pace. Systems like large language models can already engage in complex reasoning, write code, analyze data, and generate creative content. While current AI isn't conscious or truly intelligent in the way humans are, the trajectory is clear. Within decades, we might develop artificial general intelligence that matches or exceeds human capabilities across all domains. AI doesn't face the same limitations humans do. An AI doesn't need oxygen, food, or water. It doesn't suffer from isolation or boredom. It doesn't age or deteriorate from radiation exposure. An AI could theoretically operate for centuries without maintenance, making it ideal for long-duration space missions. We could send AI explorers to map the galaxy while humans remain safely on Earth. But this raises its own questions. If we send AI to explore the stars, are we really exploring? Or are we just sending our tools to look for us? Is there something essential about the human experience, about physically going places and directly witnessing wonders that can't be captured by sending machines in our place? Some argue that physical human presence is essential, that we have a duty or destiny to spread beyond Earth, to ensure humanity's survival by becoming a multi-planetary, even multi-stellar species. This perspective sees human expansion into space as a continuation of our evolutionary history, the same drive that led our ancestors to explore every corner of Earth. Others argue that sending humans across the stars is unnecessary and perhaps even arrogant. We could learn everything we need to know through robotic probes. We could listen for signals from other civilizations rather than trying to reach them physically. We could focus our resources on solving problems here on Earth rather than pursuing expensive space exploration. There's validity to both perspectives. Space exploration does consume resources that could address poverty, disease, or climate change. But it also drives technological innovation, inspires new generations of scientists and engineers, and addresses the ultimate long-term risk, extinction. Earth won't last forever. Eventually, billions of years from now, the Sun will expand into a red giant and consume the inner planets. If humanity is still around, we'll need to have left Earth long before then. Even before that cosmic timescale, there are more immediate risks. Asteroid impacts, supervolcano eruptions, pandemics, nuclear war, or runaway climate change could devastate or even destroy civilization. Having self-sufficient human colonies on Mars, in space habitats, or eventually around other stars would ensure that humanity survives even if Earth becomes uninhabitable. This is sometimes called the backup drive argument for space colonization. Just as you back up important data to protect against loss, we should back up humanity across multiple locations to protect against catastrophic risk. It's a form of cosmic insurance policy, spreading our eggs across multiple baskets so that no single disaster can wipe us out. But even with the strongest motivations, we still face those fundamental barriers. The distances are too vast, the energy requirements are too high, the timescales are too long. Unless we discover some revolutionary new physics, something that lets us bypass the speed of light limit or manipulate space-time itself, interstellar travel will remain extraordinarily difficult. That brings us back to those exotic concepts, warp drives and wormholes. Let's take a deeper look at whether these might actually be possible. The Alcubierre drive, as I mentioned earlier, would work by contracting space in front of a spacecraft and expanding it behind, creating a warp bubble that moves faster than light without the ship itself ever accelerating. Miguel Alcubierre's original paper, published in 1994, showed that this doesn't violate general relativity. Einstein's equations allow for regions of space to move faster than light relative to each other. After all, the universe itself is expanding and distant galaxies are receding from us faster than light. The Alcubierre drive would artificially create a similar effect on a small scale. The problem, as I touched on before, is the energy requirement. Alcubierre's initial calculations suggested you'd need negative energy equivalent to multiple Jupiter masses. Negative energy, or more precisely, exotic matter with negative energy density, would be needed to hold open the warp bubble and prevent it from collapsing. Later, refinements by physicists like Chris Vanden Broek and Harold White reduced the energy requirements by changing the geometry of the warp bubble. White's research at NASA, though controversial and not peer-reviewed in the traditional sense, suggested that an oscillating warp bubble might reduce energy requirements to something like the mass of Voyager 1, around 700 kilograms. That sounds much more feasible than Jupiter's mass, but there's still the problem of exotic matter. We have no idea how to create or harvest matter with negative energy density. Some quantum effects, like the Casimir effect, do produce negative energy on incredibly tiny scales, but scaling this up to move a spacecraft is purely hypothetical. Moreover, even if we could create a warp drive, there are serious concerns about unintended consequences. Some physicists have calculated that the process of creating and collapsing a warp bubble could release enormous amounts of radiation that would sterilize anything at the destination. Others worry about causality violations, essentially time travel paradoxes, if FTL travel becomes possible. General relativity allows for closed, time-like curves, paths through space-time that loop back on themselves, enabling time travel. If you could move faster than light in certain reference frames, you could potentially create these loops, arriving at your destination before you left. This creates paradoxes like the famous grandfather paradox. What happens if you travel back and prevent your own birth? Most physicists believe that some unknown principle, perhaps connected to quantum mechanics, prevents these paradoxes from occurring in reality. But until we have a complete theory of quantum gravity that unifies general relativity with quantum mechanics, we can't be sure. The universe might simply forbid warp drives through mechanisms we haven't discovered yet. Wormholes face similar challenges. Einstein and his colleague Nathan Rosen showed in 1935 that the equations of general relativity allow for bridges connecting distant regions of space-time. These Einstein-Rosen bridges, or wormholes, could theoretically allow instant travel between 2 points that are light-years apart in normal space. But naturally occurring wormholes, if they exist at all, would likely be microscopic, unstable, and impossible to traverse. Making a traversable wormhole large enough and stable enough for a spacecraft requires exotic matter with negative energy to prop open the throat. Once again, we're stuck needing something we don't know how to create. There's also the problem of creating a wormhole in the first place. You can't just dig a hole through space. According to current theories, you'd need to manipulate the quantum foam, the seething quantum fluctuations that might exist at the Planck scale, around 10 to the minus 35 meters. That's 20 orders of magnitude, smaller than an atomic nucleus. We have no technology even remotely capable of manipulating space-time at that scale. Some theoretical physicists have proposed that advanced civilizations might find natural wormholes created during the Big Bang and somehow stabilize and enlarge them. Or perhaps microscopic wormholes constantly appear and disappear in the quantum foam, and with sufficiently advanced technology, one could be captured and grown. But these ideas remain purely speculative, more science fiction than science at this point. Kip Thorne, the Nobel Prize-winning physicist who consulted on the movie Interstellar, has done serious work on traversable wormholes. His research shows that if exotic matter exists and can be controlled, wormholes might be possible. But he's also clear that we have no evidence exotic matter can exist in the quantities needed, and no idea how we'd manipulate it even if it did. The same physical laws that seem to permit these shortcuts through space-time also seem to make them impossibly difficult to create and maintain. It's as if the universe is taunting us, showing us possibilities that remain forever out of reach, theoretical curiosities that can exist on paper but never in reality. This pattern appears repeatedly in physics. The equations allow for many things that we never observe: naked singularities, time machines, perpetual motion machines that exploit quantum fluctuations. But nature seems to have built-in safeguards, principles we call cosmic censorship, chronology protection, and thermodynamic laws that prevent these mathematical possibilities from manifesting in the real world. Stephen Hawking famously proposed the chronology protection conjecture, suggesting that the laws of physics prevent time travel and the paradoxes it would create. While this remains unproven, it reflects a deep intuition that the universe is consistent, that it doesn't permit contradictions or logical impossibilities. Perhaps the speed of light limit serves a similar protective function. If interstellar travel were easy, if civilizations could rapidly expand across the galaxy, what would prevent conflicts between expanding empires? The vastness of space and the difficulty of traversing it might be nature's way of keeping civilizations isolated until they're mature enough to handle contact responsibly. This is pure speculation, of course. The universe doesn't care about our philosophical preferences. The laws of physics are what they are, whether we find them convenient or not. But it's worth contemplating why the universe has the structure it does, why the constants and laws take the specific values that permit complexity and life, but impose strict limits on what's possible. Let's think about the anthropic principle for a moment. This principle observes that the universe must have properties compatible with the existence of observers, because if it didn't, we wouldn't be here to observe it. The fundamental constants of physics, things like the strength of gravity, the mass of the electron, or the speed of light, all have values that fall within narrow ranges that allow stars, planets, and life to exist. If gravity was slightly stronger, stars would burn out too quickly for life to evolve. If it was slightly weaker, stars might not form at all. If the electromagnetic force were different, atoms couldn't form stable molecules. The universe appears fine-tuned for life, which has led to much philosophical and scientific debate about whether this is a coincidence, evidence of design, or a selection effect from a multiverse. Perhaps the speed of light is also fine-tuned, not just for the existence of matter and energy, but for the structure of how information and causality work in our universe. If light and causality could propagate infinitely fast, cause and effect might become scrambled. The universe might not be comprehensible or predictable. The speed limit ensures that events have a clear order, that effects follow causes, that the past is fixed and the future is open. In this view, the difficulty of interstellar travel isn't a bug, but a feature. It creates isolated pockets where life can emerge and evolve independently, where civilizations can develop unique cultures and perspectives. It ensures diversity in the universe, preventing any single civilization or life form from dominating everything. Of course, this could be just us rationalizing our limitations, finding meaning in what's really just an arbitrary fact about reality. The universe doesn't owe us easy travel or convenient access to the stars. We happen to live in a universe with these particular laws, and we have to work within them, whether we like it or not. So where does this leave us? We've explored the technical, biological, psychological, and philosophical barriers to traveling 1 light year. We've seen that with current technology, such a journey would take tens of thousands of years. Even with the most optimistic near-future technology like laser-pushed light sails or fusion drives, we're still talking about decades to centuries for the nearest stars. For human travelers, the challenge is compound. We need massive amounts of energy, reliable life support, protection from radiation, sustainable food production, artificial gravity, and solutions to the psychological strain of isolation. We need to either extend human lifespans dramatically, develop reliable suspended animation, or accept multi-generational journeys where the travelers who depart are not the ones who arrive. Each of these approaches requires breakthroughs in multiple fields. We need advances in propulsion, energy generation, materials science, biotechnology, psychology, and social engineering. We need to solve problems that have never been solved before, to create technologies that push the absolute limits of what physics allows. And even if we solve all these problems, we're still bound by relativity. We cannot exceed the speed of light. We cannot cheat the cosmic speed limit, no matter how clever we are. Unless our understanding of physics is fundamentally wrong, unless there are loopholes we haven't discovered, interstellar travel will always be difficult, time-consuming, and expensive. But here's the thing, difficult doesn't mean impossible. Expensive doesn't mean it's not worth doing. Humanity has accomplished incredible things that once seemed impossible. We've split the atom, landed on the moon, eradicated diseases, connected the entire planet through a global communication network. We've sequenced the human genome, detected gravitational waves, and photographed black holes. Each of these achievements required solving problems that seemed insurmountable. Each required decades of research, billions of dollars, and the coordinated efforts of thousands of brilliant people. But we did them because as a species, we're driven to explore, to understand, to push beyond our current limits. The question isn't whether interstellar travel is possible with today's technology. It clearly isn't, at least not in any practical sense. The question is whether we'll develop the technology needed within the next century or two, and whether we'll have the will and resources to attempt it. Some people are optimistic. They point to the exponential growth of technology, the rapid pace of scientific discovery, and humanity's history of achieving the seemingly impossible. They believe that within a few generations we'll have fusion power, advanced AI, nanotechnology, and perhaps even insights into quantum gravity that could open new possibilities for propulsion. Others are pessimistic. They point out that the easy discoveries have been made, that we're hitting fundamental limits in many fields, and the progress is slowing despite massive investments. They note that we haven't returned to the moon in over 50 years, that many promised technologies like flying cars and fusion power have remained perpetually 20 years away for decades. The truth, as usual, probably lies somewhere in between. We will continue to make progress, but not at a smooth, exponential rate. There will be breakthroughs and plateaus, unexpected discoveries, and insurmountable barriers. The path to the stars, if we ever walk it, will be long, difficult, and uncertain. If you made this far, I am sure you will love this other video at the left side of the screen. How long until humans achieve interstellar travel? If we want to survive, we need to reach the stars. Here's the twist. We might not need 40,000 years. In this video, we explored why when race to interstellar travel is closer than you think. See you there.